Okay, so we have reached the last section of this chapter, and this section mainly just defines one thing, that is limit at infinity. Note that we have already seen this limit of a function f as x approaches x naught. We have already seen this when x naught is an adherent point of capital X, which is the domain of the function f, which is the domain of f. F, of course, is real valued. Now what we are going to do, we are going to consider plus infinity and minus infinity in place of x naught. And then we are going to ask the same thing. What possible meaning can we assign to this notation, this symbol? Can we somehow meaningfully define limit in that case also, or actually in two cases? Namely, here you can have plus infinity and also minus infinity. So for that, we need this first of all. X naught originally in our old definition, the original definition of limit, in that x naught is after all a real number. But now we want plus and minus infinity to be adherent points of the domain of f. So it is with that definition that this section starts. So let us start like that. This is definition 9.10.1. Let capital X be a subset of R. While defining adherent point, of course, we do not need any function, but then while defining limit, function will have to be considered. So let X be a subset of R. We say that plus infinity is an adherent point of X if for any real number m there exists x belonging to x such that x is greater than m, x exceeds m. So putting it more simply, this condition just tells us that no matter what m we choose, and in fact our tendency is towards choosing larger and larger m. No matter how large m is, x still has a larger point in it. So x is unbounded in that sense towards that side. Okay, towards the positive side of the real axis. Similarly, and when that happens, we say that plus infinity is an adherent point of x. You can understand why this definition makes sense and why this one also we are calling an adherent point. Because you see, in the original definition where x naught was a real number, there x naught being adherent to x meant what? It just simply meant that x naught is very close to x, as if it's touching x. The precise definition, of course, is that in any neighborhood of x naught, there is at least one element of x. In this case, that neighborhood of infinity, of course, I mean, we cannot define it in terms of neighborhoods that we have seen so far, but still we can kind of imagine a neighborhood of infinity to be something like this. I mean, infinity, of course, is not something that lies on the real line. It's not a real number, but it's towards that. So this is kind of a vague thing, just for us to see that this definition is somewhat like the original one itself. So plus infinity is towards that side. When we say we are taking M in R, actually what that does is that it defines a ray which goes towards that side. And that ray is this. More precisely, it is this open interval. So this itself you can call a neighborhood of plus infinity, although actually it is not, okay. But still, it is somewhat like a neighborhood of x naught, where that neighborhood looks like this. Okay, it is something that contains x naught and it is very small. This one, however, does not actually contain plus infinity. That's why I said that it's not exactly a neighborhood of plus infinity, but it is somewhat like a region that is towards plus infinity. And that region has at least one element of x because of this inequality. That's why the definition has this condition. Similarly, minus infinity is towards this side. So now we would want, again, if you choose an m, some m, in this case, the focus will be on the to the left of m. So the set is unbounded on this side. When that happens, we are going to call minus infinity an adherent point of x. The precise statement is this. Similarly, we say that minus infinity is an adherent point of x if for every m belonging to R. This m has nothing to do with this m, okay? It's another definition. Technically speaking, it's another definition. For every m belonging to R, there exists an element x in X such that X this time is less than n. Okay, so this is the definition of plus and minus infinity being adherent points of a set X of real numbers. So you can understand that the definition implies these things. In other words, plus infinity is an adherent point of X if and only if, that of course we denote by IFF, if and only if X has no upper bound in R. That in turn is equivalent to this, if and only if supremum of X is equal to plus infinity. note one thing carefully, that this definition implies that X is non-empty, although that we haven't said anything. Okay, why does it imply that X is non-empty? Because if X is empty, then for any m, then for no m you will find such an X in X satisfying this condition. Okay, let alone for all m. That is why if plus infinity is an adherent point of X, then X necessarily is non-empty. Now, why am I bringing this non-emptiness? That's because for a non-empty set, the supremum is plus infinity. For the empty set, the supremum by definition is minus infinity. So that problem is not present here. Similarly, minus infinity is an adherent point of X if and only if X has no lower bound. That this first if and only if is immediately clear from the definition, because this is precisely the case in which X is failing to have an upper bound in R. In R, I say because plus infinity is always an upper bound for any non-empty set of real numbers in the extended real number system. And the second if and only if is also clear, because in that case precisely because X is non-empty, the supremum is plus infinity. Similarly, minus infinity is an adherent point of X if and only if X has no lower bound in R, if and only if infimum of X is minus infinity. Okay, so these things immediately follow from the definition. Now let us make a remark linking this definition and the original one. Original one means we already have a definition for adherent points where those points are real numbers. So this is the remark. The remark just tells us this: the above definition may seem different, rather different actually, the author writes, may seem different from the original definition of adherent point, and that is definition 918. The definition of, let me write like this, real adherent points. So that we do not forget what this actually is. You need not go back and see what the definition is. I mean, you obviously remember. That's why we are writing like this. But can be unified. Now, you see, it can be unified. I mean, actually, truly speaking, there is no distinction between this new definition that we have seen just now and the old definition, provided we think of the extended real number system using the topological structure of that extended system. you will be able to see that the two definitions are in fact the same thing. Here only we have the points which we want to call adherent points as plus or minus infinity, the smallest and largest elements in that extended system respectively, and in the old definition we just have a real number. So the point here is that these new adherent points are also extended real numbers, and actual real numbers are also extended real numbers. And using the topological structure, we say, or the author says using the topological structure because that idea of neighborhood comes up. Okay, that's why. But we won't do this, okay. There is no need to see that these two things are the same. So what does tau say? But can be unified union. Yeah. But can be unified using the topological structure of the extended real number system R star. When you view things in light of topology, many things which may seem like totally unrelated actually become the same thing, just different aspects of the same thing. However, at this elementary stage, we need not bother too much about topology. We still have time to see why that is important. And moreover, we haven't yet seen the notion of topology itself formally. Okay, so let's just forget about those things. Of R star, but we won't do so. Yeah. We won't discuss this here. Okay, this is not the right time for that. And now we come to our actual definition, limits at infinity. Limits at infinity. Not infinite limits, okay, limits at infinity. So our x naught in this equation in this familiar equation, our x naught is going to be either plus infinity or minus infinity, not the L. That L also can be made plus or minus infinity. That is a different thing altogether. We won't need that here. Okay. So the definition, of course, starts like this. So you can imagine that actually we are going to write conditions for two definitions depending on whether x naught is plus infinity or minus infinity. Let x be a subset of R, and let us continue like this. Let x, which is a subset of R, have plus infinity as an adherent point. But before I write something else, let me also draw your attention to another thing. Had these two definitions been entirely unrelated and different, say the old definition of adherent point and this new one have no relation at all between them, then there is no reason for calling these new points adherent point, right? And that is why, because there is an underlying relation, that's why we are calling them also adherent points. Okay, so now x has plus infinity as an adherent point. Let f from x into R be a function and let L be a real number. It's important that here L is a real number, not plus or minus infinity. That's what I was saying just now. We say that fx this is a very strange way of saying this thing, but the author for some reason decided to use this word. Fx converges to L fx converges to L as x tends to x naught in x if for every positive epsilon there exists a real number m such that Tao writes the next thing in words, but ultimately that just means this, such that what he writes is that such that fx is epsilon close to L, but that just means this. If x belongs to x and x is greater than m, that is, i.e., if x belongs to x intersection this open ray, then the distance between fx and L is at most epsilon. When this happens, then we say that fx converges to L as x tends to x naught in x. And we denote this entire thing, we denote in symbols by like this, by writing our usual notation actually. Limit of f of x is L as x tends to plus infinity in capital X. Okay. So this is the notation. And this is only one half. So now we are going to also define limit of f at minus infinity. I think I need a little ink. The weather is extremely dry. Even if I do this before starting the video, it just dries up. That's the problem. And if I put too much ink, then the thing will get messy. Alright. And for the second part, we have to again write all those things. Let x, which is a subset of R, have minus infinity as an adherent point. Let f from x to R be a function and let L be a real number. There is no need to write in words, you can just write L belongs to R. We say that fx converges to L as O. Okay, see, what is x naught? It is plus infinity. This is how we make mistakes. I was thinking of plus infinity, but writing x naught is a habit. As x tends to minus infinity in x, if for every epsilon greater than 0, there exists a real number m such that fx and L are epsilon close if x belongs to x and this time x is less than n, i.e. if x belongs to x intersection the open ray minus infinity comma n, then fx and L are epsilon close. The reason we need x to have minus infinity as an adherent point for this definition to make sense is because you see, the fact that minus infinity is an adherent point of x makes these intersections non-empty. So actually, if you look carefully, you are looking at an implication here. If this happens, then this happens. If this intersection is empty, then the implication will become vacuously true. And in that case, all strange things will start to happen. For example, in that case, the implication will be true no matter what your L is. So it will be actually true for all L, and the notion of limit entirely, it is just gone. Okay. What we know or what we think limit should be, that idea itself is gone when such vacuously true implications are allowed. I mean, technically they are true, but that just makes the whole thing lose meaning. That is why, to avoid that situation, we consider minus infinity to be an adherent point when defining limit at minus infinity. This was also the case for the original definition of limit. That's why we need x naught to be an adherent point of x. We have already discussed this before. So in this case also same thing happens. We denote this by writing, again a similar notation is there. Okay, while reading you should read it like this: the limit of fx is L as x approaches minus infinity in capital X, or the limit of fx at minus infinity is L in the set X. Let us now see one example. Okay, you consider this function f from 0 comma plus infinity into r, and the rule for the function is, it's just the reciprocal function. The function is well defined because in this interval it's actually the set of all positive real numbers. Every such real number has a well defined unique reciprocal which also turns out to be a positive real number. So it's a well defined function. Note that plus infinity is an adherent point of the domain of our function. It's very easy to see. No matter what m you choose, note that our original m actually can be negative also. But whatever the case is, whether that m is negative or positive, there exists at least one real number here, a positive real number, which exceeds that m. To see why, you can apply the Archimedean principle. Okay, I am not going to elaborate more on this. You already know what to do. Our aim here in this example actually is to show that the limit of our f at plus infinity is 0. Choose any epsilon greater than 0. Let capital M be 1 over epsilon, which is a legitimate real number because epsilon is non-zero, so its reciprocal exists. Now, if x belongs to 0 comma plus infinity, and which just simply means that x is a positive real number, and x is greater than 1 over epsilon, then the distance between f of x and 0, which is this, Why were we able to get rid of absolute value? That's because x is positive, so mod x is simply x. Now x is greater than 1 over epsilon, so 1 over x is less than epsilon. But you see, what we have shown is that no matter what epsilon is, there exists an m such that if these conditions are true, actually you can write m here because we have given this a name, no? So that is m. Then fx is epsilon close to 0, but then by our definition, hence x belongs to 0 comma plus infinity, f of x, which actually is 1 over x, is equal to 0. I mean, we already know, or we can guess that this limit is 0, but now we have the precise formal definition, and using the definition, using first principle, we have shown in fact that the limit is 0. Now, it turns out that many of the things that we have seen, many of the properties of limits, not at infinity but at some real numbers x naught. We have seen many properties like algebra of limits and many other things. They turn out to be true for limits at infinity as well. But the thing is that, for instance, it turns out that all the limit laws still continue to hold, even for this type of limits. But the thing is that we won't be using these limits at infinity much, so we won't bother about them. There is one more thing, however. You see, we already have seen, way before seeing these things, limits of functions, limits of sequences, right? Limit of a sequence of real numbers an being L, and in all such limits n always approaches infinity. Now we have a similar thing. The difference is that there we had a sequence, here we have a function. Here we have plus infinity, here we have infinity. Is that a difference? No, because infinity is a simpler notation for plus infinity. It's like 2 and minus 2. 2 is actually plus 2, but we do not write the plus. Now, is a sequence also a function? Yes, it is a function. For example, this sequence is actually a function from the set of natural numbers, into the set of real numbers. So, are these two notions somehow related? And the answer is yes, they are actually the same thing. I mean, when in place of fx you have an, you will see that the limit that this definition gives you is nothing but the limit that we have already seen for sequences. This is the only exercise in this section, and it's the last one, which we will solve, of course, in the community section when the time comes. That means next Sunday. And with this very small section is over, and this chapter is also over. After this, we will start differentiation, which can be called the heart of calculus. I mean, we are doing analysis, but after all, we are doing calculus only much more rigorously than how we do calculus in school. But anyway, that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.